when we have a chemical reaction that occurs in an open container, which is very common, then the pressure is constant, but the volume might change, right? So the energy can evolve as both heat and as work. Often, though, we are only interested in the heat exchange. We don't care about that pressure volume work. So here's some more mathematical acrobatics. So enthalpy. Enthalpy is given the symbol H. We can't use E because E was for internal energy. So enthalpy is H. The enthalpy of a system is the sum of the internal energy and the product of its pressure and volume. Because they said so. Okay. So enthalpy is the internal energy, that's the energy we've been talking about, plus pressure times volume. Enthalpy, like that change in energy, is a state function. The internal energy is a state function, the pressure is a state function, the volume is a state function. It doesn't matter how you got there from one place to another, the difference is the same. So we can look at the enthalpy change, delta H. The enthalpy change would be the change in energy plus P delta V. So why isn't this delta P? Well, because we said this is occurring at constant pressure. So what's changing is the delta V, is the V. So delta H is delta E plus P delta V. Well, what does delta E mean? That's a change in internal energy. That was Q plus W, right? So that's Q plus W. Here, this isn't QV, Q at constant volume. This is QP, Q at constant pressure. And then we've got P delta V. Well, what does P delta V equal? We just talked about pressure volume work. Work equals negative P delta V. So that means that P delta V must equal negative W. Just moving the negative sign to the other side. So if this is negative W and we've got W there, then W minus W and poof, the W's disappear. They did this on purpose. So the change in enthalpy is equal to heat if the pressure's constant. But before we were looking at the volume being constant, here we're looking at the pressure being constant. This is more useful because we don't have to worry about an airtight container for this to occur in. Okay, so what is the difference between delta H and delta E? They're very similar in concept, and they're often very similar in value. And so you can actually get through this class very well, not clearly understanding the difference between them. But I'm going to tell it to you anyway, just in case you care. Delta E measures all of the energy exchanged with the surroundings, the heat and the work. Delta H measures only the heat exchanged under constant pressure. So if you're looking at something where the volume changes are small, then you're not going to see much difference at all between delta E and delta H. The only time you see really big difference is when you're looking at reactions that either consume large volumes of gases or produce large volumes of gases where that change in volume is really big. Then delta E and delta H are not going to be exactly the same. The signs follow the same conventions. So if delta H is positive, and so delta H, H means enthalpy, but it measures the heat, right? So you can think of the H as heat. That's okay. It's not technically correct, but it's okay. So delta H is positive, heat being absorbed by the system. Delta H is negative, heat being released by the system. So we have two fancy words, endothermic and exothermic. The prefix exo means to go out or to be on the outside. So there's an exit sign on the door because that's where you go out, right? And endo means coming into endothermic heat coming in, okay? We started this chapter talking about chemical hand warmers, the iron filings being oxidized in an exothermic reaction. So delta H for that reaction is negative because heat is going out. Your hands experience the heat coming in. There are also chemical cold packs. So, these are often found in first aid kits. And you get this little pouch, and you break something in the middle and mix these chemicals together, and it gets cold. It's an endothermic reaction. It gets cold because it's sucking energy from the surroundings. So this is an endothermic process. The hand warmer is an exothermic process. A flame is also an exothermic process. It's releasing heat into the surroundings. Okay? Okay, so let's identify each process as endothermic or exothermic and indicate the sign of delta H. Okay, an ice cube melting. And we're talking about the ice cube. So is the ice cube getting heat or releasing heat? It's getting heat. So an ice cube melting is an endothermic reaction. This can be a little tricky to think about. How do you make an ice cube melt faster? Raise the temperature. Yeah, if you stick it on a saucepan in the stove and light the burner, will it melt faster? Yeah, because you're putting more heat into it. That'll help us identify. That's an endothermic process. So if it's endothermic, what's the sign for delta H? Positive. So delta H is greater than 0. It's a positive number because heat's coming into the system. When money comes into my wallet or my account, that's positive. Nail polish remover, acetone, quickly evaporating after it's accidentally spilled on your skin. Have you ever done that? Or in lab, have you ever gotten acetone on your hand? What does it feel like? It feels cold. Why does it feel cold? It's at room temperature. Because it's evaporating. When you get all sweaty, like I am right now, and you get a breeze, which I don't have, how does it feel? It feels cool, right? Because it's the water evaporating off your skin. So the nail polish here is what we're looking at as the system. But we don't know, we can't identify or talk to the nail polish remover. What we experience is our skin. Our skin experiences a cooling effect. Right? So that means that the heat is leaving our skin and going into the nail polish. So for the nail polish, this is endothermic or exothermic? Endothermic. And because it's endothermic, delta H is going to be positive, greater than 0. Okay. Gasoline burning within the cylinder of an automobile engine. Well, anything burning, what do we experience as if we are part of the surroundings around something burning? We experience heat. Our hands get hot. So is heat leaving the gasoline or going into it? It's leaving it. It's going into our hands, but it's leaving the gasoline, so that's an exothermic process. And for exothermic, the sign of delta H is negative. Delta H is less than 0. It's a negative number. What makes this confusing is there's always a system and a surroundings. And what's endothermic for the system would be exothermic for the surroundings. If the system is exothermic, then the surroundings are endothermic because the heat leaving has to go into something. It leaves one and it goes into the other. And so you need to make sure that you're looking at the correct part. Molecular view of exothermic reactions. So an exothermic reaction gives off heat. It causes the temperature of the surroundings to go up. That energy comes from stored chemical potential energy within the reactants. So gasoline has a high potential energy. It's not very stable. In the process of the chemical reaction, that chemical energy is turned into thermal energy. And that generally occurs because bonds are broken. Where's my pointer? Well, oh, there it is. Existing bonds in that compound are broken, and new bonds are being made. But the new bonds have less potential energy than the old ones, and the difference is released into the surroundings. So here the products have less chemical potential energy than the reactants did, and the difference is released. Endothermic reaction is the opposite. So with an endothermic reaction, the temperature of the surroundings goes down. So that ice pack, instant cold pack, you hold it and your hand gets cold. Why does your hand get cold? Because heat is leaving your hand and going into the chemical reaction. So it's an endothermic reaction. In the course of that reaction, existing bonds are broken, new bonds are made, but the new bonds are higher in energy than the old bonds. And where does it get the energy? It gets the energy as heat from the surroundings. So it pulls energy in from the surroundings. And then you have the products of the reaction having more potential energy than the reactants. Anybody have any questions about that? It's so quiet. Okay, so enthalpy change for a chemical reaction. So we said that enthalpy is a capital H. So delta H, enthalpy change for the reaction. We often call this the enthalpy of reaction or the heat of reaction. This is an extensive property, meaning it does depend on how much stuff there is. If you burn 2 drops of gasoline or 2 gallons of gasoline, you're going to get a different amount of energy released, right? So by convention, we calculate delta H, the heat of reaction, based on how we've written out the chemical reaction. Because this is the heat of reaction, so we've got a chemical reaction that we're looking at. So here's the chemical reaction for the combustion of propane. So in this reaction, 1 mole of propane is burning. Here, the heat of reaction is listed as negative 2,044 kilojoules. Well, that would change if you had more propane or less propane. So how much propane is this referring to? It's referring to the amounts given in the reaction in moles. So that would be for 1 mole of this. 5 moles of oxygen, 3 moles of carbon dioxide, 4 moles of water. This relates to the molar amounts in the chemical equation. We did it that way because it's convenient. So 1 mole of propane would release 2,044 kilojoules of energy. Or if we were measuring the oxygen, for every 5 moles of oxygen consumed, we'd release 2,044 kilojoules of heat. So let's apply that. Ammonia reacts with oxygen according to this equation. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. Well, we're told that there's 155 grams of ammonia. This ends up being a stoichiometry calculation, but we don't have moles in the middle. We don't have moles of this to moles of something else. This number relates to each of these separately. So the minus 906 kilojoules is for 4 moles of ammonia. So I can convert any of these quantities in any of these in moles to heat directly. I don't have to go mole to mole. So what I'm going to do here is I'm going to start with grams of ammonia, and I'm going to convert to moles of ammonia. I'll try. And then I can go directly to kilojoules, because the relationship here is given there. This amount of heat for 4 moles. But I do have to find out the amount in moles. So I've got 155 grams of NH3. Need moles. I've got grams in the denominator. And check my math, but 17.034. And then kilojoules and moles in the bottom. So it's this amount minus 906 for every 4 moles of ammonia. Should probably specify that. And so moles of ammonia cancel out. So I've got 155 divided by 17.034 times negative 906. Three sig figs minus 824, 4.1. Kilojoules. When I round that, because I'm rounding in the tens place, I need to be careful. I can't round 8,244 to 824. So if you tend to make that mistake, put this in scientific notation. I can round this to minus 8,240 kilojoules. Any questions? So it says calculate the heat associated. Do I really need this negative sign? Does associated with tell me what direction the heat's going? No. Yeah. I forgot to divide by 4. You are exactly right. You win the prize. Unfortunately, I have no prize. Thank you very much. Okay, let's fix that. How about minus 2061.0? Better? 3 sig figs, so minus 2060 kilojoules. We need the negative sign here. If it said calculate the heat released by the complete reaction, then we would make it a positive number. If I say, how much money did you spend? You give it to me in a positive number, even though it was a negative thing in your checking account, right? Here's a random thought. Why do we still call them checking accounts if we don't use checks much anymore? Do you think we'll ever change the name of that? If you don't have checks, can it be a checking account? Random thoughts.